In the previous video, we have discussed a one-to-one invertible continuous map, which translates the material point in its original initial configuration to its current position. So the capital X represents the initial coordinates of the material point, and small x represents the current coordinate of the material point. And we've discussed the function of deformation grading, which relates a line segment in its initial configuration to itself in the current configuration. All right. Then we introduce the Green-Lagrange strain, which is a measure of the deformation of this line segment in terms of change in length. It's a nonlinear strain measure because it's a nonlinear function of displacement. Now we've talked about points, we've talked about line vectors, line segments, and we've talked about the change in length of this line segment. Next, we are going to talk about volume change and surface change, and we're going to express them mathematically across the two different configurations. All right, from vector calculus, we know that a differential volume like a cube like this can be expressed as dx1 cross product with dx2 and then dot product with dx3. Similarly, we can express the same thing for dv, which is the same cube but transformed in the current configuration. So here we would write d small x1 cross product with d small x2 and then dot product with d small x3, except that now I'm going to make use of the deformation gradient so that we can directly write it this way. Right? So deformation gradient times d capital X1 would give me d small x1. All right. So this is directly the form that we want, so that we can express dv, which is the same volume in the current configuration, in function of the deformation gradient and the vector in the initial configuration. If we a bit of calculation, let's say we set the magnitudes of these vectors to be 1, so dx1, dx2 and dx3, these scalar magnitudes, let's set them all equal to 1. Then the first one, you would obtain the first column of f. For the second one, you would obtain the second column of f. And the last one, you would obtain the third column of f. When you take the first column of f and cross product with its second column, and then dot product with its third column, you obtain the determinant of f. So basically, you can do this exercise yourself and verify that dv can be expressed as the determinant of f, the deformation gradient, times dv0. This is the relationship between the differential volume in the current configuration and in the initial configuration. Okay, so determinant f relates the change of differential volume. Now, having discussed about the change of a volume, a small volume, let's move on to discuss the change of a small surface. We are going to take the same surface here facing us. So this surface, which is oriented, it has a surface area of dA0 with a normal n0. It will be transformed into dA with a normal n in the current configuration. We know that the relationship between dv and dv0, which I've just obtained, and from vector calculus, we know that n0 times dA0 is simply this term here. And similarly, n times dA is simply this term here. All right, and now we make use of this relationship. We multiply the dv0 by determinant of f. We obtain this expression. And we know that this must equals to dv, because determinant of f times dv0 equals to dv. So we just set the two equal, and we substitute nda in this expression, and we obtain this expression. So these two must be equal. Next, we're going to do a bit of manipulation. We change the dot product into matrix multiplication. So we are going to take this one and replace this column vector by a row vector. And what we do is we make the transpose of it. Similarly, we do the same for this one, so make the transpose of it. So the dot product now becomes a row vector multiply a column vector. So this is a standard mathematical manipulation for dot product. Now I'm going to further expand this term. So I bring out the dx3e3, so I have its transpose, and then I shift the f to the back of it, so I have a f transpose. So this is what you would obtain if you were to expand this term. Now I can highlight a few things here. I have determinant of f n0, determinant of a0, da0. I have this one. On the left of both highlighted terms, you have the same term, dx3e3 transpose, dx3e3 transpose. So this equation needs to be valid for arbitrary surface, arbitrary domain of this differential volume, and for arbitrary surface with arbitrary normal. So in this case, for illustration purpose, I've chosen the normal to be along the 3 direction, but in a different coordinate system, this could be really of any direction. So this equation needs to be valid, and I need to have these highlighted terms to be equal. Basically, if I move the f transpose to the left side of this equation, I can obtain that nda equals determinant of f, which is scalar, I bring it forward, f transpose inverse times n0 da0. This is a so-called nonsense formula, which relates an oriented surface from its initial configuration to its current configuration. So now we have discussed everything in terms of kinematics, from point-to-point map, to a mapping between line segments, to strain, which discusses the change in length, to determinant of f, which relates the change in differential volume, and then to a nonsense formula, which describes the change of an oriented small surface. Okay, this is a summary of what we've covered. We started with discussing different configurations. We have the initial domain and boundary, which is known to us. We have the current domain and boundary. Then we have the initial coordinates of a point, of a material point. And then we have the current coordinates, right, which is a function of the initial coordinate and time. And then we have the displacement, which is simply the difference between small x and capital X. And we have the deformation gradient, and it can be written as an identity matrix plus the displacement gradient. We have the Green-Lagrange strain tensor. It is independent of rigid body rotation, therefore it's suitable for geometrical nonlinear. It's symmetric, and it applies on quantities defined in the initial configuration, which means that, remember, when we want to get a strain along a particular direction, we pre and post multiply the E, which is a Green-Lagrange strain tensor or matrix, by d capital X hat, which is the unit vector of a line segment in the initial configuration. Then we have determinant f, which describes the change in volume, and nonsense formula, which describes the change in an oriented surface. So this is a summary of all the kinematics description in the frame of 3-dimensional geometrical nonlinear deformation.